Salam and welcome back to our corrosion series. My name is Fatima Garba Yusuf and this is Khalil Chronics. So here we're going to solve an example that involves corrosion density, corrosion current, and overall corrosion rates. So the question says a mild steel tank 80 cm high with 25 cm by 25 cm bottom filled with aerated water up to 50 cm level shows a corrosion loss of 256 grams over a 5-week period. And then you are asked to calculate the corrosion density, the corrosion current, and you are given additional information that you should assume that the corrosion is uniform across all surfaces and the mild steel tank corrodes in the same way as pure iron. Now don't just take this information for granted, especially when they said the corrosion is uniform. It means that it's not pattern corrosion, it's not crevice corrosion, it's uniform corrosion. That means you don't need to consider that the corrosion is more concentrated in a particular section of the tank or something like that. And then we're told that the mild steel tank corrodes in the same way as pure iron. Now here, instead of you trying to think of, oh, how many electrons should I be considering, because they said pure iron is iron 2, that's the iron that hasn't been oxidized, so you can simply be able to use the characteristics of iron whenever you need something of that nature. As for the formula that we're going to use the formula of weight loss. We can see that we have already been given our weight loss. This is our W. Then this 25 cm by 25 cm is the dimension of the base of the mild steel tank, and this is the height of the tank. But then we're told that the water, the aerated water, just reached the 50 cm level, so that means it wasn't filled. And this will come into play when we're calculating our surface area. So when we say we're going to calculate our solution, you can draft this out somehow. Let's start with the square bottom. Let's say this is 25 by 25, the square bottom, and then it's a tank, so it goes upwards like this, like this. So if we assume that up to this point is our 80 cm mark, something like this. So if we say this is 80 centimeters, that's the whole height is 80 centimeters, but we can recall that we're told that the water just reached the 50 centimeters. That is just more than half. So something like this, let's say this is 50. So it means that our water reached just this area. Something like this. So let me shade the occupied area. So that means if we're to bring out the covered portion, it will be something like this. Right, with this 25, and this 50. So we're asked to calculate the corrosion density and the corrosion current. In this case, the formula we are going to use is this. That's W equal to ITM divided by NF, or AITM divided by NF. So it depends on which one you decide to calculate first. For example, if you are going to take this as your section A and this as your section B, then calculating your corrosion density implies that you should use this first. That is, you are going to equate W equal to AITM over NF and then make your small letter I the subject of the formula. as you can recall, our corrosion density is equal to corrosion current divided by area. So it will be more comprehensive for you to first find your corrosion current, that's using this formula. Since we have our W given as 256 gram, we're going to use our mass for iron, then we're going to use our number of electrons for iron, we're going to use our Faraday constant, and we're going to use our time, 5 week. We'll convert it to seconds and then calculate our capital letter I. So here we have 256 gram equal to our I multiplied by your 5 is going to be converted to seconds. This is in weeks, right? You have to convert it to 7 and you multiply it by 7 so that it will be in days. From days you move toward hours. You convert, each day has 24 hours. From hours you convert it to minutes. From minutes you convert it to seconds, right? Then your mass is going to be 55.855 grams per mole. That's 55.855 gram per mole. This is in seconds, this is in amperes, and this is in gram. So you now divide this divided by your N, number of electrons is 2, and your Faraday constant is 96,500. Now we imputed all these values because our T is equal to 5 weeks, our N is equal to 2 electrons, our F is equal to 96,500 coulombs, our M is equal to 55.855 grams per mole. Alright, so you now use your calculator and you calculate the value of your I. To simplify your work, you can cancel out some values before making your I to be the subset of the formula. For example, you can cancel a 0 here, a 0 here, another 0 here, another 0 here, and of course 2 into 2 is 1 and 2 into 24 is 12, right? Then also 5 will go into 965 to give us 193, so that we don't have our values to be too large. So there we go, 193. Now to make our I the subject of the formula, we simply take the values here and multiply them to this one. This is 256 over 1, right? So you cross multiply and you isolate your I. So you have 256 multiplied by 193 is equal to all these values multiplied by I, right? But since we are trying to make our I subject of the formula, we will divide by the value so that I will be left alone, right? So we have 5 has been cancelled. We have 7 times 12 times 6 squared, because we have 2 6's, then times 55.855. Let me show this here. So we'll go on to multiply and divide. 193 multiplied by 256 divided by 7 divided by 12. So we'll multiply the terms in the numerator. So we multiply the terms in the numerator and divide them by the terms in the denominator. 256 times 193 divided by all this, and your I in the end will turn out to be 0.2925, that's 293. 0.293 amperes. As for your corrosion density, you simply divide your corrosion currents by your area. But what is your area? Now in this case, you are not going to consider the whole tank, because not the whole tank is actually exposed to a corrosive environment. Instead, you're going to consider this one. And to do that, you calculate the area of this base and then add it to the area of each of these faces, these 4 standing faces. Of course, the top is open, there's no metal covering the top here. Hence, your area, your corrosion area, is going to be, of course, 25 by 25 centimeters squared for the base. This is for the base, while for the sides you have 50 by 25 for each of them, and there are 4, so it will be 4 times 50 by 25, right? And this one is also in centimeter square. This one is for the sides. So our 25 by 25 will give us 625 centimeters squared, equal to 625 centimeters squared, plus our 50 by 25 will give you 1250 multiplied by 4. That's 5,000 centimeters squared. (5,000 centimeters squared). If you add them, they will give you 5625 centimeters squared. In any case, you can decide to convert this to standard units, MKS units, SI units. Instead of using centimeters square, you have to convert it to meters square, since our other values are also in standard form. Hence, you can convert this to centimeters squared by dividing by 100 squared, right? And this will give you 0.5625 centimeters squared, meters squared, sorry. And this will give you 0.5625 meters squared. And for you to just calculate your corrosion density, you simply divide what you got as your corrosion current by your corrosion area. So if you use your value in centimeters squared, it will be in amperes per centimeter squared, and if you use your value in meters squared, it will be amperes per meter squared. So here we go. So your corrosion current I is going to be equal to 0.293 amperes divided by, let's say, 0.5625 meters squared. That will be 0.521 ampere per meter squared. And that's it. You can also try using the per centimeter squared, and as long as you input your appropriate units, it's alright. So that's all for this question, and see you in the next video.